What sort of things might reasonably be expected to affect the period of a mass spring system? Well, you might expect the mass to do so, because the heavier the thing is, the harder it is to move around, the more effort the spring has to put in. The spring constant, because obviously the springier the spring is, the stiffer the spring constant, the faster it can snap things back and forth. And you might imagine the amplitude of the motion, the more distance it has to cover during one full period, might influence how long it takes. But in fact, not all of them do actually have an influence on the period. We may go back to saying, by Newton's second law, the net force is the mass times the acceleration. But we know the net force is minus kx, and we know that the acceleration was minus a omega squared cos omega t. So we find out that k over m is omega squared. This is called, and then we say, well, omega is 2 pi over the period, so omega squared is 4 pi squared over the period squared. We then plug in our omega that we just found from over here. And eventually we get down to that the period is 2 pi root of m over k. And that's an important thing to understand. Most important thing to notice from it is that it does not depend on the amplitude. The period of the system is determined entirely by how heavy the mass is and what the spring constant is. This behavior is, in broad strokes, pretty easy to understand. The more massive the object, the more inertia it has, the harder it is to move it, and therefore the longer it takes. It doesn't get to as high a speed. Based on some amount of energy you have, it gets to a lower maximum speed, so therefore a lower average speed overall, etc. It takes longer to execute one swing. And then the spring constant makes sense because the stronger the spring, the more easily it is pulled back, or from a given distance, the more energy I have stored, and therefore the greater the kinetic energy, the greater the average velocity is going to be, the more easily it crosses out. It's sort of interesting that the amplitude drops out. The amplitude doesn't matter because in stretching the spring longer, it definitely has more distance to cover during a period. If we double the amplitude, now we have doubled the distance it covers, but we've also stored more energy in the spring, so the velocity ends up being higher on average. And it turns out those two things cancel out. All right, so let's just do a quick example of that. Draw a blue circle around the spring or springs with the greatest period and a red circle around the spring or springs with the least. We'll take this as our base. So that's just k and m. We remember that t is 2 pi root m over k. So if I increase the denominator by a factor of 2 but don't change the numerator, then I get a square root of 2 on the bottom, which of course is less than 1. If instead I go back to the original and I multiply the top and bottom by the same number, in this case 4 and 4, that factor cancels out and I have the same period. So this is also 1, whatever it was before. And then if I increase the top, but I don't do anything to the bottom, then I end up getting a factor of root 2. So we see that the greatest is this one, and the least is this one. And then kind of interestingly, these turned out to be the same, but they're neither the greatest nor the least. All right, a mass spring system consists of a mass of stiffness K and equilibrium length L, connected to a cart of mass M resting on a horizontal frictionless surface as shown. If the cart is pulled to one side a small distance and released, it oscillates back and forth with amplitude A and frequency F. Which do each of these actions do to F? What's going to happen to F? Before I dive into that, we might want to go back to the period. Oops. Is 2 pi m over k, which implies that the frequency, which is 1 over the period, is 1 over 2 pi root k over m. So that's what I want to look at. So if I increase m, it's on the bottom, a bigger number on the bottom makes the smaller thing out. So we would decrease f. The larger m, the longer the period, which we talked about before, which means the lower the frequency. If we increase k, on the other hand, we're going to have the opposite effect. If we pull back a little further before release, then we're essentially increasing a, and we know that has no effect. The amplitude does not impact the period, so it does not impact the frequency. if we increase k, that's going to make f larger. If we decrease m, it's going to make f larger, and therefore this will just increase f. And then here, for the last one, we know that it doesn't matter what we do to a. So we're really back on the line with increase m, so we should get something like this.